Hello, Randall Youngblood. Myself, along with Ruth Andrews and Jeff Chase, would like to present Adapting Old with Renew, the Hughes Warehouse Makeover. During this presentation, I will discuss the background, scope, and some of the sustainable materials used on the project. Jeff will be discussing energy conservation and savings, and Ruth will talk about the occupancy comforts of the building and how they contribute to the worker productivity.
Methods and sources for this project were site visits to multiple adaptive reuse projects, interviews with building occupants and city officials, and traditional research collected through library and online sources for information on this project.
Located in downtown San Antonio's Riverwalk area is a Hughes warehouse that was built in 1917 for storage of plumbing supplies. Overland Partners, an architectural firm, ventured into an adaptive reuse project in 2012. They transformed a dilapidated warehouse into a 26,000 square foot sustainable architectural studio. The newly renovated facility received the 2015 American Institute of Architects Committee on Environment Top 10 Award for efforts incorporating architectural design and sustainability principles. There's a perception of owners and investors that modernizing older structures and making them high-performance buildings is costlier than new construction. However, after collecting information on 3 adaptive reuse projects, our research revealed costs for adaptive reuse projects average the same or below the average cost of commercial construction, which ranges between $160 and $170 per square foot. In fact, the Hughes Warehouse project costs less than $70 a square foot. Construction cost is not the only benefit of adaptive reuse. According to the EPA, 534 million tons of construction and demolition waste was generated and placed in landfills in 2014 alone. 90% of that debris comes from construction demolition. Adaptive reuse projects effectively reduce the debris deposited into landfills and significantly reduce the embodied energy consumed to construct and operate a new building. The project kept in place the existing 196 cubic meters of double brick perimeter wall structure. The effort saved $270,000 in demolition and new construction costs, effectively keeping over 200 tons of debris out of the landfill. Additionally, keeping the walls in place reduced the embodied energy needed to construct a building by 1,011 gigajoules. The other example of embodied energy savings are the Green Building in Louisville, Kentucky, and Warner Red Factory in Washington, D.C., which saved an estimated 1,622 and 2,014 gigajoules of embodied energy, respectively. Both buildings combined kept over 1,400 tons of construction debris out of the landfills. In order to lower the heat island effect of the structure, a reflective thermoplastic polyolefin cool roof was installed over the entire surface, creating a solar reflective index of 98.6. A benefit of a warehouse adaptive reuse is that most of the early 1900s warehouses were outfitted with clear-story windows. That early design helps to provide natural daylight into the facility. In addition, architects designed a partial frontal punch-out of the eastern-facing wall to allow for additional daylighting. The clear-story window frames were modified to match the frontage window framing, and both were outfitted with 1-inch thick Solar Band 70XL low-E coated high-performance glass. In addition, window shades controlled by an astronomical clock were installed along the clear-story windows. This allowed control of the sunlight into the building depending on the sun's angle in reference to the building. Controlling light enables the facility to maximize sunlight and reduce energy needed for the lighting of the facility, improving overall energy efficiency. Now, Jeff will discuss in more detail how the installation of these materials contributed to energy efficiency.
Thank you, Randy. Energy efficiency for an older facility can be a challenge. One of the benefits of adding new windows at eye level is that occupants can now have a view to the outside. At the Hughes Warehouse, bringing natural lighting into a building was crucial. Over 77% of the lighting is not in use during daytime hours. With the installation of a new energy-efficient HVAC system and the clear-story windows being operable again, indoor air quality is at 100% of the time below desired CO2 levels. 60% of the occupied space is within 15 feet of an operable clear-story window to let fresh air in. Monitoring plug loads and remotely turning off outlets from data analysis of occupancy sensors located in occupied spaces. Advanced power strips look like standard power strips but can turn off power to any additional outlet or combination of outlets on the power strip. The strip turns off the power delivered to itself to eliminate any phantom load usage. Schedule timers, motion sensors, and remote switches are other few devices that can be used for control. The design team of the Hughes warehouse explained they overlooked planning for a phantom power usage, or more commonly known as plug loads. A plug load is the amount of energy drawn by a device plugged into an electrical outlet. Plug loads constitute a substantial portion of the electrical demand in a commercial building. Phantom loads occur when electricity flows through any plugged-in devices, such as computers, monitors, printers, networking equipment, when they are not in use. Advanced sensors and controls continue to decline in cost and are relatively easy to install in building retrofit projects. Low-cost sensors, controls, and retrofit BAS can also reduce building energy consumption by 20 to 30% in small and medium commercial buildings, representing a 0.3 to 0.4 quads in total energy savings. Stanford University conducted a plug load study of 220 campus buildings in 2014 and determined that laboratory equipment consumes 50% of total plug load electricity, accounting for 11% of total campus electricity consumption. Currently, plug loads make up 5% of primary energy consumption in U.S. commercial buildings. However, as HVAC and lighting systems become more efficient, plug loads represent a growing proportion of total building energy use. Although they are typically one of the last end user considered for energy conservation, plug loads alone can contribute up to 50% of total energy use in high performance buildings. As plug loads continue to increase in commercial buildings, it is important to understand how to successfully manage them, especially in reduction of wasted energy linked with plug loads. While a combination of measures can be taken to minimize plug loads, there is also an important end factor: the educating of people who must play a role in the control and management of plug loads in their daily work routines. Now Ruth is going to talk about occupancy comforts.
Thank you, Jeff. Today I'm going to review some new recommendations for the Hughes warehouse building owners with regards to occupancy comforts. As reviewed in our previous presentation, the post-occupancy survey result was overall very good at 80%, but our team chose the top 2 areas of dissatisfaction to research and recommend ways of improving these scores. As you can see on the slide, these 2 areas are acoustics and thermal comfort in summer. It's no surprise that acoustics was listed in the top 2 areas of dissatisfaction on the survey. Regardless whether the office type is private, open, high or low partition cubicle offices, acoustics is the biggest source of dissatisfaction in LEED certified office buildings according to UC Berkeley surveys. There are several factors employed by Hughes warehouse designers that contribute to the noise level or lack of speech privacy, such as daylighting, active and passive heating and cooling systems, as well as abundant use of hard surfaces inside the building. There are many solutions to improve the rating, such as relayout of the workstations, installing acoustic baffles, or other sound absorbing or blocking materials. The thermal comfort recommendation I'd like to share with you would be integrated control of building solutions that affect temperature, humidity, illuminance, and CO2 levels, as you can see on this chart on the page T, H, I, and C. As seen in the survey, air quality was very good, but thermal comfort was not. Typically, active and passive sources of heating, cooling, lighting, shading, and ventilation are controlled independently. However, we would suggest integrated controls to optimize the system to improve occupant satisfaction and cost savings. Fine-tuning these sources should occur regularly as part of the building's commissioning. In conclusion, Hughes Warehouse is a building that proves that adaptive reuse projects can work. The project delivered on cost, responsible material use, energy savings, and customer satisfaction. This case study used the methods of site visits, interviews, research, and analysis to draw conclusions and make recommendations to the Hughes Warehouse building owners and other owners looking to see if they can transform their property into a sustainable landmark. The 3 areas covered today can be summarized in 3 main statements. First, Materials by Randy. Employing adaptive reuse versus new construction is a way to significantly reduce the amount of embodied energy consumed on a project. Second, Energy by Jeff. Do not discount energy savings that can be achieved by installing sensors and controls that reduce phantom load. Third, Occupancy Comforts by me, Ruth. All the sustainable solutions have to work together in an integrated manner for complete occupant satisfaction. This concludes our case study on Hughes Warehouse. Thank you for your attention.